This lecture is about hybridization. Hybridization is the combination of two or more atomic orbitals to form hybrid molecular orbitals of the same energy and shape. Recall from introductory chemistry that you have the s, p, d, and f orbitals. In organic chemistry, we usually just talk about the s orbital, remember that's spherical in shape, and the p orbital, which is dumbbell shaped. P has the px, py, and pz orbitals, all of which are orthogonal to each other. Now the simplest example is hydrogen, molecular hydrogen, and two hydrogen atoms overlap to form one molecule of hydrogen. Hydrogen has just one valence electron, and that exists in an s orbital. So if you think from a molecular orbital point of view, you have two s orbitals that overlap, and that results in the formation of the sigma bond to make molecular hydrogen. In organic chemistry, the simplest molecule is methane. Methane is CH4, and we're going to first look at the ground state of carbon. Remember that carbon has 4 valence electrons in its outermost shell, and if we fill in the electrons from the lowermost energy to the highest energy, we are left with 2 unpaired electrons. Now this would imply that carbon can make only 2 bonds. We know that's not true. We know that we're making CH4, which implies that carbon is going to make 4 bonds. And so instead of looking at the ground state, we're going to now look at the excited state of carbon. In its excited state, we now have 4 unpaired electrons, and that means we can form the expected number of bonds, which is 4. The only discrepancy here is that, according to this model, you would expect carbon to form 3 bonds that were of equal length and 1 bond that is shorter. Experimentally, though, all 4 bonds are of the same length. Now, where does this leave us? This leads us to hybrid orbitals. The true picture here is that we're not using just the s and p orbitals to form bonds. We are actually forming hybrid orbitals from these s and p orbitals. So if we mix one s orbital and 3 p orbitals, we would end up with 4 hybrid orbitals that are all sp3. These are 4 degenerate orbitals, that means they are all of the same energy, and they all look like this. Now let's go back to methane as our example. The carbon in methane is sp3 hybridized. What does this mean? It means that we've used one s orbital and all 3 p orbitals of that carbon to form 4 hybrid orbitals that are all sp3. When we add in 4 hydrogens that are going to bond with their s orbitals, we end up forming 4 sigma bonds. Sigma bonds are formed by head-on overlap of these orbitals. Let's also tie in geometry here. For an sp3 hybridized carbon, the geometry around that carbon is tetrahedral. This means that the bond angle around here is going to be 109.5 degrees. Now let's move on to sp2 hybridized carbons. The simplest example is ethene, which is C2H2. And in ethene, an sp2 hybridized carbon is going to use one s atomic orbital, combine it with 2 p atomic orbitals in order to get 3 hybrid orbitals, all of which are sp2. It then uses these sp2 hybrid orbitals to form 3 sigma bonds. Again, sigma bonds are formed by head-on overlap. And remember that it still has one p orbital that's been unused. And this p orbital is going to be used to form the pi bond. And remember that pi bonds are formed by sideways overlap of orbitals. If we think about the geometry of sp2 hybridized carbons, the geometry is trigonal planar, and in this case, the bond angle is going to be 120 degrees. Finally, let's talk about sp hybridized carbons. The simplest example is ethine or acetylene, which is C2H2. And in an sp hybridized carbon, the carbon is going to utilize one s atomic orbital and one p atomic orbital to make two hybrid orbitals, both of which are sp. It's going to use these two sp orbitals to make two sigma bonds, one to the hydrogen that's adjacent to it and the other to the carbon that's adjacent to it. And remember that it's got two p orbitals that are unused, and these two p orbitals are going to form these two pi bonds by sideways overlap. The geometry of sp hybridized carbons is linear, and it's got a bond angle of 180 degrees. This wraps up the review on hybridization. We will discuss more examples in class.